Okay, great. So I'm honored to be here today and to be able to talk about both making the manufactured future, how artificial intelligence may be able to accelerate us into that manufactured future, but also most importantly about what this may mean for the future of US jobs. I personally I grew up all of my life in Reading, Pennsylvania. I don't know if anyone knows Reading. It's, if you've ever played Monopoly, the Reading Railroad. It's not the Reading Railroad, it's the Reading Railroad. That's where I grew up. And Reading was the height of industrial prosperity in the 1930s. It had textiles, steel mills, it had automotive shops, and the railroad was bringing that across the country. By the time I was growing up in Reading, and even more so by 2011, Reading was the most impoverished city in the nation. Anyone have a guess of how many people live in poverty in Reading? Over 41% of people live in poverty in Reading, Pennsylvania. So I didn't know this while I was growing up. I just thought Reading was cool and I had friends and life was good. But what was happening and what's been happening in our country is that you see that there has been a massive shift in the location of manufacturing activity from the US. So just looking back 15 years, in 1999, 6% of manufacturing was in China, and 26% of manufacturing value added was in the United States. And by 2013, only 16% of manufacturing value added was in the United States, and 24% of that manufacturing value added was in China. And really it is the exponential rise of both demand and production in China that leads to this shift. The interesting thing is we're not actually making less in terms of, not necessarily by products, but in terms of value added. So our manufacturing value added in the United States has remained approximately constant and slightly risen, although the number of jobs has slightly declined, and not by much. And so you might at first glance say, okay, well, I guess we're making about the same value added, so maybe life's all good. But bigger concerns start to arise as we think about what this may mean for national security. For example, IBM selling off its last trusted foundry, the US's last accredited trusted foundry to global foundries, what this might mean for our capability to innovate. So if you don't have manufacturing here, I'm actually going to use the example from Stefan from yesterday. You can't imagine asking a chef to be able to create a fantastic recipe if you remove him from his cooking place and his oven. And so a question then, if we want to increase manufacturing in the United States, is how do we increase or further increase the US's proportion of manufacturing out of that global pie, which is increasingly getting bigger. And with that, our national competitiveness, our capability to innovate, and our national security. And so I'd like to propose to you today that the answer to that cannot alone be to be more productive. We can't just be more efficient. We can't not be more efficient. We also need to be efficient, but we also need to make products that are made nowhere else in the world and everyone wants to buy. So if you are making the products that lead the world, and everyone wants to buy from you, then you have jobs. That's how it works. So let's talk a little bit about how this unpacks in the context of the future of advanced manufacturing. So a lot of people may have seen the study that came out that looks at where the iPhone today is manufactured. So it's actually manufactured entirely in developing East Asia and assembled over in developing East Asia. They did a kind of a sourcing, one of the consulting firms, of tracing this back. And what's interesting about this is that all of those components are commodities. These are not the types of advances that you've heard today from Stefan, from Citrine, from Liz, across the board. And so In contrast, if you imagine this iPhone, instead of being made by a bunch of assembled products, being made now as a watch, do you have those slap wrists? Anyone have kids? You know, they have the little slap bracelets at home, right? So you take a slap bracelet, you slap the watch onto your wrist. It's made out of flexible polymer electronics. Then you take it back off your wrist, you unfold it on your table, and now you have your computer. If that's the watch of the future, that is fabricated without assembly, and that can only be made right now here. So if you think about whether it be that watch, but interestingly enough, many of our materials and process innovations enable us not just to remove the need for assembly, but to make products with performance, whether it's the GE nozzle that takes us from 20 to 1 parts, but is also dramatically lighter weight, uses dramatically less fuel, also a national security interest. Whether it's, again, composites for automobiles, where we're taking 120 parts and 140 inserts and switching that to just 7 or 9 or 12 parts for the entire vehicle. And flexible electronics, where instead of thousands of parts making up your electronic components, you're fabricating it all as one. In all of these cases, what they share in common is not just less assembly, but also higher performance in various fashions. In other words, no one else can make them based on our extraordinary engineers. They also share that the process is the product. The chef needs to be in the kitchen, and that this is where we can lead going forward in the future. So the question of what this means for jobs is not a simple one. And I want to give you 2 examples just to point out how complex these second-order effects are. So the first example, you may laugh, but we're going to go to Lapland in Finland. So in Finland, up through the 1960s, the way you herded reindeer and the way everyone made their livelihood was herding reindeer. And they skied next to the reindeer, and they would take about 4 days to get across the country. And then in 1961 or 63 approximately, they realized that there was a snowmobile. And this snowmobile could change their lives, right? And so everyone, all families, when you got married, you got a pack of reindeer, and that's what how life proceeded. And so in comes the snowmobile, and suddenly now we are, instead of taking 4 days to get across the country to do the type of travel that you need on skis, now they're driving after the reindeer with the snowmobiles. But this had created incredible problems, in the sense of now the reindeer are scared, they're running up onto the hillsides, they no longer know which reindeer is owned by who, so they have to barter them off at auctions, and within 7 years, you go from every family owning reindeer and having a livelihood with reindeer to only 3 families in the entire region owning all of the reindeer and having all of the capital, and extreme wage polarization. So the others are out of work, they're thinking about going into cities, and so forth. In contrast, and you would think, everyone thought this was great, we're gonna be more efficient, life's better. In contrast, if you look at the ATM teller example, right? So here we're introducing ATMs. Everyone was afraid we're putting all of the tellers out of work. But instead what happens when ATMs are introduced is suddenly the banks are able to open more branches. And instead of us putting what seems like an automatic replacement for the ATM tellers, more people out of work. Instead, we actually have more branches, and tellers move into new jobs where they're now more in a customer service type of relationship and sort of managing. So you end up with more branch tellers in the short term in this example. And so we have more jobs and increased production in this case. These relationships are not things easy to guess. So what we've been doing in a way that we uniquely and only can at Carnegie Mellon is we've been saying, how can we take existing engineering models, detailed operations models, and look at the implications of these types of technology change for the worker? And so what we've done to date is we've said, okay, let's look at this massive consolidation of parts that's happening across aerospace, across communications and semiconductors, across automobiles, across a vast array of our major economic drivers in the economy. And interestingly enough, in our preliminary results at this point in time, there are fewer steps, but these products, so not even taking into account the fact that you may now be selling the products instead of someone else and the extra jobs that might come there. But there are fewer steps, but we've found that there are higher skilled steps on the shop floor. So instead of being stuck in an assembly facility where you're doing root jobs over and over again, there's more testing jobs, there's more technician jobs, and there's more engineer jobs. And if you add to that, and this is where you get into dark magic, the fact that before you weren't making anything, and now you're making everything, you start to push towards increasing not only your global share, but the jobs that you have on the shop floor. So this sounds great. We should push forward. And I think you can guess at this point, given the topic, where we're going to end. We should push forward these technologies, but these technologies that would let us win at the global race face a lot of challenges. They have extreme time delays to bringing them to market. There's problems with venture capital, there being enough financing of advanced manufactured products. And in my own work, we've shown that when you move manufacturing overseas into assembled instead, even though you have higher performance in the other products, it can be so cheap to do those assembled products that it delays or reduces incentives to produce the most advanced technologies. And so what we've been doing at Carnegie Mellon, I was fortunate to participate in the last year, is looking at the extraordinary opportunity that AI provides to us to bridge the valley of death and accelerate bringing these new products to market, a lot of which you've heard about today. So from accelerating materials and process discovery, like what Liz Holm is doing, to identifying, leveraging machine learning jointly with experts to identify where you could put these new materials and products, like metal additive manufacturing, to reinventing, so as Liz was talking about, in real time, changing the processing that you're doing so that you can fix the part as you're making it in terms of manufacturing systems and deployment, to enable more people, like you've heard from Upskill, to participate in the workforce. And also we need to bring in policymakers. Today, for example, the FAA has told us it will be more than 10 years before they could bring computational models into their government decision making. And yet, if you're having Citrine create new materials and processes continually, and Liz being able to get those products ready to go out the door faster, we need to bring those types of techniques into government decision making. And we need to seed at the interfaces so that, just like GE was talking about with Stefan Biller, this is one continuous process that feeds back to itself and really lets us get those products of the future out the door. That's it.